to welcome you all. So today's session is about magnetism. Okay, so magnetism, magnetic materials. So magnetism is one of the very important topic in condensed matter physics. Okay, so what is magnetism? Magnetism is the force exerted by magnets when they attract or repel each other. Okay, so magnet is the So magnetism is the force exerted by magnets when they attract or repel each other. See, if you consider the whether this magnet may be the natural magnet, bar magnet, or it may be the electromagnet. Okay. So bar magnet, this is a bar magnet, and it contains the two pole, north pole as well as south pole. So electromagnet is nothing but a solenoid. Okay, current carrying loop. It created the magnetic field, and it is a magnet. It is also act as a magnet. Okay, so it is nothing but a So if you connect these two terminal in the battery, it will create the magnetic field, and it is also act as a magnet. So this is the magnetism. Okay, so magnetism has fascinated mankind for thousands of years. Okay, so probably the first magnetic material is to be probably the lodestone. Okay, magnetite. The chemical formula is Fe3O4. So why it is fascinated mankind means it is so unusual property. Okay, so if it is there any unusual property or something, usually human or people will attract easily each other. Okay, so usually magnet means it's like a magic type only. Okay, so why do we bother about magnetism, or why do we study about magnetism? So since it is a if you consider the modern today modern devices, it is most of the devices it is related on the magnetic materials. See, for example, microphone, loudspeaker, electric motors, transformer, sensors, NMR. It is a very important analytical tool to understand about the structure, dynamics, topology of the particular molecules. Okay, and it is a components. Okay, all the functional groups also we have to identify. Okay, so next one is MRI. It is a very important non-invasive imaging tool. Okay, so since it is not related to the any radiation type, so it is we can repeatably we can take it out. Okay, so this is very important in the medical field. Okay, so then if you consider the maclotrine, okay, which is magnetic levitation. Okay, maclotrine. And even cell phone. Okay, all we are without cell phone we cannot almost not possible to uh, almost not possible to handle the modern technologies. Okay, so for example, cell phone have a namely niobidium, okay, neodymium iron boron magnet we are using, okay. So whether directly we are using the bar magnet or solenoid magnet we are using, okay. So electromagnet we are using, okay. So in order to understand the magnetic properties very clearly, to study as well as we have, if we are study very clearly, then we can designing our materials, magnetic materials as well as magnetic applications. So in order to know very clearly, we can understand the magnetic materials as well as magnetic properties, okay. So what are magnetic materials? Magnetic materials are which can be magnetized when introduce the magnetic field, okay. So what are magnetic materials? So materials which can be magnetized in an external magnetic field. In other words, the magnetic materials, when we introduce the magnetic field, it may repel or attract each other, okay. So for example, some example for magnetic materials, okay. Iron nails, okay. Nickel paper clips, steel coin, whereas non-magnetic material, if we take the paper, plastic, wood, so etc, okay. So usually we play the magnet with our school life, okay. So keeping the paper, we have to keep the bar magnet in the bottom side, and some of the iron particles are small magnetic particles we keep with the upper side, okay. So we have to play right like this, all we played, okay. So it is a magnetic field can transmit to the non-magnetic material also, okay. So that's what we understand, okay. So in order to understand the magnetic materials or classification of magnetic materials, some of the basic terminology are there, okay. So we have to first we have to look at there, then we will go to the classification of magnetic materials, okay. So let's start with the magnetic lines of force, okay. So consider the bar magnet. So if you consider the bar magnet, so this is the north pole and this is the south pole. So as we know that the magnetic lines will start from like this, okay. It is a continuous curve, okay. okay. So it is like a continuous one, okay. So like this, okay. So this is for typical bar magnet, okay. Whereas in the case of electromagnet, if you consider any current loop, okay. So you consider the, I will consider the one copper one coil, okay. Okay, if you consider this is a anti-clockwise, the start from here, S and N, okay. Okay, so this is the how the magnetic, these are all magnetic lines of force, okay. These are all magnetic lines of force, okay. Okay, so what is the magnetic field, okay. If you consider the bar magnet, the around the bar magnet where the magnetic effect is felt, okay, where the magnetic effect, okay. So this region, okay, if you consider, if you consider any magnetic material, if you consider here, it will be attracted, okay. So if you, for example, take it as a ferromagnetic material, okay, it is attracted, whereas if you keep here, it may not attracted, okay. So only the region where the magnetic effect is felt, okay, this region only the magnetic field, okay. So magnetic field usually they will notify as a H, okay, or intensity of magnetic field or magnetizing field, okay, all these all are same only, it is denoted as a H, okay. So unit is Tesla, we can say, okay. Okay, so next we will see about the magnetic dipole moment, okay. Or simply they will call it as a magnetic moment, okay. So if you consider the bar magnet, okay, so dipole moment is nothing but a product of pole strength, okay, then distance between the two poles, okay. So m is equal to pole strength, okay. For example, I will notify as a Pm, okay, pole strength into distance between the pole, okay, poles, okay. So this is 2L, okay, because from center to this one is L, okay, this is L and this also L, okay. So this is very similar to electric polarization type only. The only thing is here we cannot separate the monopole, whereas in the case of electric charges we can separate the charges plus as well as minus, okay. Whereas in the case of magnetic dipole moment we cannot separate the poles, okay. So that is the main difference, remaining all same only, okay. As we know already, if you cut any bar magnet, what will happen? You cut into two, whether it is a n or this is a s, not like that, okay. So again it will be the n and s, okay. So that is the idea, okay. okay. So whereas in the case of, if this is a bar magnet, okay, whereas in the case of electromagnet, okay, so n is the number of turns, okay. I is the current, A is the area, okay. So this is the magnetic type of moment. This is a very important, because this is a base for magnetic materials or magnetism, okay. Okay, next we will see the magnetic flux, okay. It is usually denoted as pi. So this is a uniform magnetic field. Okay, so number of magnetic lines over the surface, okay. So number of magnetic lines over the surface, it is called magnetic flux, okay. The unit, okay. It is known as the magnetic flux, okay. Unit is Weber. Okay, so next we will see the magnetic flux intensity, or magnetic field intensity, or magnetic induction, okay. Or density of magnetic flux, okay, or intensity of magnetic flux. Usually it is denoted as B, okay. So here we are going to specify the area, okay. So number of magnetic lines over the unit area, okay. So it is usually called B is equal to pi by A, okay. See, for example, if you consider this rectangular bar, okay, so magnetic lines are moving like this, okay, so like this, okay. If we consider only this part, okay, how much magnetic lines are going, okay. So we are specifying the area, okay. So that's what here, B is equal to pi by A, okay. So unit is Weber per meter squared, or we can say Tesla. So usually in magnetic materials, usually they will use both magnetic units, for example CGS unit as well as SI unit, okay. You can keep any one of the unit, okay, for standard, because in research also they will use any standard units, okay. So no need to be confused, okay. So next we are going to see about the magnetic permeability, okay. So what does it mean permeability? Permeability means it is a ability to permit of something, okay, over the area, okay. So what does it mean? Magnetic permeability means how well it is ready to allow the magnetic lines of force, okay. So that is the magnetic permeability, okay. It is denoted as mu. Okay, so it is directly proportional to the how much field we are going to apply. See, B is directly proportional to the H, okay. So if you remove the proportionality, B is equal to mu H, okay. So mu is equal to B over H. Mu is the magnetic permeability, B is the magnetic induction, H is the applied magnetic field or magnetizing field, okay. So unit is Henry per meter, okay. So this is a magnetic permeability, okay. So there are two other permeability are there, namely mu naught and mu r, okay. So mu is the magnetic permeability of any material, okay, medium or material we can say, okay. Mu naught is the magnetic permeability of vacuum, mu r is the relative permeability, okay. Initial days, usually magnetic materials are classified based on the magnetic permeability only, okay. So these days it is since we introduce more number of magnetic materials and modern devices, modern characteristics, now they are using the with respect to magnetic dipole moment, okay. Whether it is a permanent magnetic dipole moment are there or not, like that we will discuss in later, okay. Mu r for free space, okay, mu r for free space is 1. So mu r for air, okay, is approximately 1. So depends upon the relative permeability we can classify the materials, okay. For example, mu r greater than 1 or mu r less than 1, these are all under the certain category, okay. Mu r greater than 1 is for example paramagnetic, very greater than it is a ferromagnetic, like that, okay. If it is mu r less than 1, it is under the category of diamagnetic material. We will see the later, okay. So next we will see the magnetic susceptibility, because magnetic permeability and magnetic susceptibility both are very important terms in the understand about the magnetism, okay, or magnetic properties of the material. It is denoted by chi. So what is susceptibility? Okay, susceptibility in the sense how well it is influenced. Okay, For example, those have a low immunity power, it is easy to catch the diseases. Okay, so how easy to susceptible. Okay, so magnetic susceptibility in the sense, with respect to magnetic field, how easily it will be aligned the spin. Okay, so that's what we are going to see. Okay, so susceptibility is, it is a conversion. Okay, it is a ratio of magnetization over the how much magnetic field we are applying. Okay, so magnetization in the sense, it is a converting process of non-magnetic material into the magnetic material. Okay, so M is the magnetization. H is the applied magnetic field. Or magnetizing field. Okay, so it is a measure of how much material magnetized in the application of applied magnetic field. Okay, or external magnetic field. Okay, so this is also very important, and now we are going to see the relation between the permeability and susceptibility. Okay, so here there is no unit. Okay, so dimensionless unit. Okay, so these two sometimes the students will confuse. Okay, permeability as well as susceptibility. So permeability means how much it is allowing, okay, magnetic flux lines, whereas in the case of susceptibility means how much it is magnetized. Okay, so that is the idea. Okay, so now we are going to see the relation between the so magnetic permeability and susceptibility, Okay, okay. So if you consider the solenoid, okay, for example, for electromagnet we are considering. Okay, if you consider the solenoid, okay, so current is in here, and the current coming out. Okay, so this is a solenoid, it is nothing but a copper coil like. Okay, so if you connect this with the battery, okay, or we can say for easy to understand, battery. Okay, so due to this battery, it will create the magnetic field. Okay, so due to this, magnetic field is created. Okay, so for that magnetic field, B0 is equal to mu naught into Ni A. Okay, so number of turns as well as how much current we are giving, and the over the area. Okay, so which is nothing but mu 0 H. Okay, so now we are going to introduce the one ferromagnetic material. Okay, okay, so due to this magnetic field, the ferromagnetic material start to magnetizing. Okay, so due to that magnetizing field, okay, so that is internal magnetic field, we can write it as a mu 0 into how much magnetizing. Okay, mu 0 into M. Okay, so this is the equation 2. So from the equation 1 and 2 we can write it as, So total, okay, total magnetic field. Which is equal to outside plus inside, okay. So which is mu 0 H plus mu 0 M. If you take it out the common, mu 0 H plus M, or in other words mu 0 H, if you take it out, 1 plus M over H, okay. So we know that M over H is the susceptibility, okay. So now we can write it as okay. So we can say this is the equation 3. So we know we know that the permeability, okay. So we know that the permeability, okay. So B proportional to H and B is equal to mu H and mu is equal to B over H, okay. Or here, okay, this is enough, okay. So B is equal to mu H, okay. So from equation 3 and 4 we can write it as mu H is equal to mu 0 H 1 plus susceptibility, okay. So we can write it as a mu in terms of mu r, okay. So mu naught into mu r, H is equal to mu 0 H 1 plus psi. So now we can cancel out. So mu r is equal to one plus susceptibility, okay. So this is the relation, okay. So since it is a magnetic permeability as well as magnetic susceptibility is very important, it can vary, okay. Mu can vary, okay, with respect to temperature, where we are going to keep the material, okay. So that place, okay, depends upon the place, okay, where we kept, okay, where we so like that external stimuli will play the role, okay, as well as magnetic susceptibility also. It is with respect to temperature, with respect to with respect to applied magnetic field, it can vary, okay. So susceptibility also can vary, temperature, field, like that, etc., okay. So because these are all very important while classification of the magnetic materials, okay. Okay. So now we are going to classify the magnetic materials, okay. So since more magnetic materials are introduced and more characterization also introduced, so now we are going to classify as a with respect to permanent magnetic moment, okay. So okay, can be classified as two category, okay. One is having a permanent magnetic moment, okay. Okay, so having permanent magnetic moment will come under the category of paramagnetic, ferromagnetic, ferrimagnetic, or we can say first antiferromagnetic, and ferrimagnetic. Whereas in the case of not having permanent magnetic moment, it is a diamagnetic. Okay. So depends upon the permanent magnetic moment, we are classified as a two category. Okay. So now we are going to classification of materials based on the how it is varying with external magnetic field. Okay. So broadly we can classify it as three. In fact, strictly speaking, we can classify it as a five category. Okay. So first let us see the broadly. Okay. So three categories we are going to see now. Okay. So I think it will be better for keep the tablet column. Okay. So this is diamagnetic. Okay. So first consider number one. Okay. Diamagnetic don't have a permanent magnetic moment. Okay. Okay. Whereas in the case of paramagnetic, permanent magnet are there. Okay. Permanent magnetic moment are there. Okay. And here also it will be there. In fact, here intrinsic permanent magnetic moment also there. Okay. So okay. So second one is without applying field. Okay. H is equal to 0. How the spin alignment we are going to see. Okay. So if H is equal to 0, so there are no spin alignment. Okay. So since H is equal to 0, there are no spin alignment in the case of diamagnetic. Whereas in the case of paramagnetic, it is like a randomly oriented. Okay. Whereas in the case of ferromagnetic, it is there is a since it have a domain factor, it have a intrinsic magnetic moment, and the spin alignment also will be there. Okay. So it is not like a random. Okay. So something like this. Okay. So third one is when we are going to introduce the magnetic field, external magnetic field. Okay. So how the magnetic alignment. Okay. So H is not equal to 0. Okay. So in diamagnetic material, the magnetic moment will repel, okay, in the external magnetic field, okay. So it is repelling, okay. When introduce the external magnetic field, it is magnetizing, and due to this magnetization, it is repelling the external magnetic field, okay. So if you consider this is the field direction for magnetic applied magnetic field. Okay, something like this, okay. So if we consider the paramagnetic, so H not equal to 0 if this is the applied magnetic field. So it is aligned, okay, it is aligning towards the external magnetic field, okay. So something like this. If you remove the external magnetic field, obviously it is a random orientation in the case of paramagnetic, okay. Whereas in the case of ferromagnetic, it is strongly aligned, okay. If this is the field direction, so almost perfectly it will be aligned, okay. So this is feeble repulsion, okay, or weakly repulsion, whereas in the case of paramagnetic it is a feeble attraction, okay, whereas in the case of ferromagnetic it is strongly attracting, okay. Okay. Okay, if we consider the permeability, relative permeability mu r, it is less than 1, okay, whereas in the case of paramagnetic it is mu r is greater than 1, okay, whereas in the case of ferromagnetic mu r much greater than 1, okay. Okay, so if we consider the susceptibility, so this is small and negative, okay, whereas here small and positive, whereas in the case of ferromagnet it is a susceptibility is much greater than, okay, so it is a large and positive in the order of 10 to the power 6, okay, so that much powerful, okay. If we consider the temperature, okay, temperature they play the role, okay. If you consider the diamagnetic, it is independent of temperature, okay, so independent. Whereas in the case of paramagnetic it is a dependent, okay, so we can say chi proportional to 1 over T, okay, so it is inversely proportional to the temperature. If you remove the proportionality is equal to C by T, so C is the Curie constant where T is the absolute temperature, okay. Whereas in the case of these are all, yeah, these are all obey the for paramagnetic, okay, whereas in the case of ferromagnetic this also will be obey, and some of the depends upon the material, we can say chi is equal to, chi is proportional to, or we can say directly chi is equal to c by t minus theta. Okay, so this is usually they will call the modified Curie-Weiss law. So chi is the susceptibility, c is the Curie constant, t is the absolute temperature, where theta is the Weiss temperature. Okay, so depends upon the theta value, we can identify the how nearest neighbor nearing atoms are, whether it is aligned parallel or anti-parallel. Okay, so this is the case for ferrimagnetic as well as antiferromagnetic also. Okay, so here theta will be play the role. Okay, so theta, if it is negative, it is more favorable to align the antiparallel manner. Okay, antiparallel. Okay, whereas in the case of theta is positive, this is parallel alignment. Okay, so it is independent of temperature, here dependent of temperature, as well as here also dependent of temperature. Okay, okay, so for example for diamagnetic. Okay, diamagnetic we can say bismuth, gold, copper, silver, okay, etc. Water, air, we can say. Okay, so whereas in the paramagnetic material, aluminum, oxygen, okay, titanium, etc. Okay, whereas in the case of ferromagnetic material, Fe, Co, iron, cobalt, nickel, steel, and gadolinium, Gd. Okay, etc. Okay, so these are all under the category. For example, all superconductors under the category of diamagnetic only, but reverse is not true. Okay, so all magnet need not to be a superconductor. Okay, here there is no Curie point type. Okay, where in the case of diamagnet, but if you consider the superconductor, there is a critical temperature are there, very low temperature. Usually there is no Curie point. Okay, no critical, we can say critical point. Okay, whereas in the case of paramagnetic, here also there is no Curie critical temperature. Even towards up to 0 Kelvin also it is a paramagnetic states are there. Okay, so here also no critical point. But whereas in the case of ferromagnet, we can say there is a critical temperature or Curie point are there. Over the Curie point, it is a paramagnet, whereas in the case of below the Curie point, it is spins are aligned towards aligning the ferromagnet. Okay, so here there is a Curie point are there. Okay, okay. So for example, there are two main characteristics are there. Okay, with respect to temperature or with respect to field, we can identify the magnetization. Okay, for example, this is MT curve. Okay, magnetization with respect to temperature. Here field is applied field is constant. Okay, right, H is constant. Okay, so how the diamagnetic will be there means it is a negative. Okay, susceptibility, this is susceptibility, it is negative. Okay, very meager, so we can say like this. okay, whereas in the case of paramagnetic it is a m over h, it is exponential decay, okay, like this. There is no such Curie point are there, okay, here also, okay, whereas in the case of ferromagnet, okay, so this is the Curie temperature Tc, okay, which means below this, okay, above this Curie temp, this is a temperature, okay, temperature in Kelvin, okay, so this is the magnetization, okay, so above this Curie temperature it is a paramagnet, okay, spins are randomly oriented, okay, whereas from this point it is started, this is a onset point we can say, okay, so from here below the temperature it is start to align the ferromagnetic wave, okay. If you consider this is the applied magnetic field H, okay. So this is the onset point, which means start to align, okay. So very low temperature only it will be like this, okay. Whereas in the case of m over h, okay. So this is with respect to temperature, right. So similarly we can see the m versus h also we can see, okay. Which means at constant temperature, okay, T is constant, okay. So here it will be like this, okay, negative like this, okay. So whereas in the case of paramagnet it is like a, it is obey the y equal to mx plus c like this, okay. Whereas in the case of ferromagnet these are a linear type, okay, whereas in the case of ferromagnet it is not linear, okay, it is a non-linear type, so that's why it is called, it is a hysteresis loop will come, okay. Okay, so starting to 0 and this is a saturation point, so this is the retentivity and this is the cohesivity, okay. So if you have, okay, this is the ferromagnetic, so for example if you consider the start to increasing the magnetic field, it is in the low region, okay, low magnetic field it is obey the linear type, okay, whereas in the case of if you increase the H, okay, it is like a non-linear behavior will come, and once it is reached the saturation, furthermore it is not able to play, okay, which means if you increase the H also it won't change the value, okay, it is a saturation, okay. Okay, so retentivity in the sense, for example, when H is equal to 0, okay, if you remove the field, but magnetic material won't lose their magnetization even in the absence of H is equal to 0, okay. So this is called retentivity or remanent polarization or remanent magnetization, okay. So this region, okay. So if you want to magnetization come to 0, we have to apply the negative magnetic field. Okay, so if you apply the negative magnetic field, so when Hc, when it is reached, magnetization is reached to 0, that is called cohesivity. Okay, so this is retentivity. This is cohesivity. Okay, so similarly negative cycle also there. Okay, similar. Okay, so this is such maximum. Magnetization maximum. Okay, similarly here also negative cycle are there. Okay, so if you consider the antiferromagnetic material and ferrimagnetic material. Okay, see, for example, if you consider antiferro. Okay, so usually without applied magnetic field, it is random orientation only. Okay, okay, whereas in the case of ferrimagnetic, so there is a residual magnetic moments are there. Okay, so it is like a ferromagnetic, but magnitude is less. Okay, if you apply the magnetic field. Okay, it is perfectly aligned the opposite way. For example, okay, whereas in the case of ferrimagnetic also opposite orientation only, but magnitude is different. Okay, okay, so this magnitude will be the role. Okay, so that's why it is ferrimagnetic. Okay, so here permeability is relative permeability, it is greater than 1. Okay, but very meager, very feeble. Okay, whereas here mu r is much greater than 1. Okay, in the order of 1000 or more. Okay, if you consider the susceptibility, it is a positive but very feeble. Okay, very meager. Okay, it is a positive, very small. Okay, so 10 to the power minus 5 to 10 to the power minus 3, but positive. Okay, whereas in the case of ferrimagnetic, it is a in the order of 10 to the power 3 or 4, like this. Okay, so here also temperature dependence are there. Okay, so it will also obey the chi is equal to c by t as well as chi is equal to c by t minus theta, both are we can apply. Ferrimagnetic also we can apply c over t minus theta. Okay, so depends upon the theta value, already we discussed. If it is negative, it is under the antiferromagnetic. If it is negative or positive, both are possible in the ferrimagnetic material. Okay, so for example for antiferromagnetic is MnCr, MnO, nickel oxide, etc. Whereas in the case of ferrimagnetic, Fe3O4, Fe2O3, ferrites, garnets, all are example for ferrimagnetic. Okay. So the magnetic moment arises. See, origin of magnetism is, there are, even though strictly speaking we can three we can say, so but mainly it is contributed to the spin magnetic moment. Okay. So electron spinning. Okay. So spinning and orbital also. Okay. So predominantly spin magnetic moment will be play the predominant role, whereas in the case of orbital magnetic moment also there it is the some extent. Okay. Whereas nucleus also there is a magnetic moment are there, it is very very less. Okay. We can negligible. Okay. So predominantly magnetic moment from the spin. Okay. At some extent. Okay, we can take the orbital. Okay. Okay, so this is the main concepts. Okay, so thank you all.